The universe is stitched together by a fabric we cannot touch, a fabric that bends, stretches, and folds in perfect silence. And somewhere in that silent architecture lies a question older than stars themselves. What happens when space-time opens a doorway and connects two distant places through a single impossible bridge? Tonight, we drift into the mystery of wormholes, the most dangerous shortcut in the cosmos, pathways that may exist only for an instant, or may never exist at all. Tunnels carved not through space, but through the geometry beneath it. Quiet, invisible, and still beyond our reach. Before we begin, if this calm journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep this small corner of the universe glowing, and it means more than you know. Now, we drift into part 1. Part 1. What is a wormhole made of? A wormhole is not a tunnel carved into space. It is a distortion of space-time itself, a bending so extreme that two distant points touch. If you could watch space-time as a flexible sheet, you would see it curve inward like a throat, forming a passage that links here to somewhere impossibly far away. But beneath that quiet curve lies the same law that shapes every orbit and every star: gravity folding the universe into new geometry. To understand what a wormhole is truly made of, we have to begin with the nature of space-time itself. Einstein taught us that space and time are not separate arenas. They are a single fabric, woven together so tightly that the motion of matter bends the flow of time, and the rhythm of time reshapes the distances between things. Everything that exists, every atom, every photon, every planet, and swirling galaxy is suspended in this fabric. It is smooth, silent, and usually unimaginably stable. But under the right conditions or the right mathematics, this fabric can buckle, twist, or fold onto itself. When physicists speak of wormholes, they are describing one of the most dramatic ways this fabric might fold. Imagine gently pressing two distant parts of a sheet together until they touch. The sheet itself is unchanged except at the place where your fingers meet. A wormhole is like that. Two regions of space-time brought into contact by a deeper curvature beneath the surface. In normal space, the distance between these 2 points might be measured in light years. Inside the wormhole's geometry, that distance contracts to something you could traverse in moments. But this is where the idea becomes subtle, because the universe does not allow such distortions easily. Gravity, the very force that shapes space-time, usually encourages collapse. When a massive star dies and falls inward under its own weight, space-time curves so sharply that not even light can escape. This is the birth of a black hole, a place where geometry reaches its breaking point. In Einstein's equations, a wormhole is like a black hole's mirror image. Possibility, not a collapse inward, but a bending that connects instead of trapping. To see the difference, imagine the mathematical description of a black hole. Its curvature draws everything inward toward a singularity. A wormhole, however, resembles two such curvatures joined at their narrowest points, like two black hole throats that meet, forming a bridge instead of a trap. In theory, this bridge could allow something to pass from one side to the other. Yet in practice, the structure is so delicately balanced that the slightest disturbance would cause it to pinch shut. So what is a wormhole made of? Not matter. Not rock or dust or particles. It is made entirely of curvature, geometry shaped into a tunnel. The material of a wormhole is space-time itself. But curvature alone is not enough to hold such a structure open. According to the mathematics discovered in the late 20th century, a stable wormhole requires something extraordinary: negative energy. Not the absence of energy, but a type of energy that moves opposite to what we expect. Unlike normal matter, which attracts through gravity, negative energy would push space apart. It would act like pressure supporting the throat of the wormhole, preventing it from collapsing under the universe's natural tendency toward contraction. This negative energy is more than hypothetical. Quantum field theory predicts that in tiny regions of space, energy can fluctuate. In some rare microscopic moments, the energy density can dip below zero. The Casimir effect, observed in laboratories, demonstrates this. When two uncharged metal plates are placed extremely close together, the quantum fields between them thin out, producing a measurable negative energy density. It is a faint whisper of the kind of physics a wormhole would need. But a real wormhole would require negative energy on astronomical scales, far beyond anything the Casimir effect can supply. To sustain a wormhole large enough for even a speck of dust to pass through, you would need fields shaped with precision we do not yet possess, energies arranged in patterns we do not yet know how to create. The exotic matter that could stabilize a wormhole is theoretically allowed, but practically unreachable. Still, the mathematics remains consistent, and that consistency is what keeps the idea alive. In physics, a structure that is mathematically possible is worth exploring, even if nature rarely assembles it. The universe contains many things it does not build easily. Neutron stars balanced on the edge of collapse, gravitational waves rippling across billions of light years, even the subatomic fields that create matter from the vacuum. Wormholes sit among these possibilities, not forbidden, simply demanding conditions that we have not yet witnessed. If a wormhole ever existed, what would its throat look like? Not a glowing tunnel, not a swirling vortex. The interior of a wormhole is simply another region of spacetime. The curvature does not shine. It does not announce itself. To any traveler inside, the journey might feel strangely calm. No jolt of acceleration, no sensation of forward motion. You would follow a natural path through the geometry, much like a satellite drifting along Earth's gravitational curves. The wormhole itself guides you, not your engines. And yet, even with this calmness, the forces at play would be immense. Near the throat, space-time curves so intensely that normal intuition fails. Tidal forces might stretch or compress objects depending on the wormhole's shape. Light entering at slight angles would spiral, producing eerie distortions of the stars behind you. In some models, photons can orbit the throat endlessly, trapped in perfect loops created by the geometry's symmetry. A wormhole might appear from the outside as a dark sphere surrounded by a shimmering halo of lensed light, a silent echo of the cosmic bending that lies beneath. The most fascinating question is whether wormholes can be traversed at all. Many solutions to Einstein's equations predict that wormholes exist only instantaneously. They flicker into being and then vanish before anything can cross them. These are quantum wormholes, microscopic and ephemeral. They thread through spacetime like tiny bubbles in a stormy sea, forming and collapsing in trillionths of a second. They are too small for atoms to pass through, too chaotic to survive long enough for structure or stability. But some theories allow for more enduring wormholes. Traversable wormholes require negative energy to counteract their tendency to collapse. If such exotic matter existed in abundance, or if civilizations could engineer spacetime at a fundamental level, these passages might remain open. Their throats would have shape, their mouths would have location. They would be bridges instead of bursts. In this sense, the answer to what is a wormhole made of becomes more than geometry. It becomes a statement about balance. A wormhole is made of spacetime curved inward, supported by negative energy pushing outward, held in tension between collapse and expansion. It is a structure built not from matter, but from the competing tendencies of the cosmos. And at its core, a wormhole is made of possibility, the possibility that the universe is not limited to the long, slow paths between stars, but might allow shortcuts through its deepest geometry. As we continue this quiet journey, one question naturally follows. If a wormhole is made of spacetime itself, then what allows such extreme bending to happen in the first place? Now we drift into Part 2. Part 2. Why did Einstein believe wormholes could exist? If you trace the equations of general relativity far enough, gravity becomes more than a force. It becomes architecture. In 1935, Einstein and Rosen found a solution to those equations that looked like a bridge, a thin connection between two regions of spacetime. They called it an Einstein-Rosen bridge. To them, it was a mathematical curiosity. To us, it became the first whisper that shortcuts through the universe might be possible. To understand why Einstein believed such bridges might exist, we have to step into the world he built, one where gravity is no longer a mysterious pull, but the gentle curvature of space-time itself. In this view, every planet, every star, every black hole is not acting through invisible force lines. Instead, each object is dipping into the fabric of the cosmos, shaping the pathways that everything else must follow. Space bends, time stretches, motion becomes geometry. Einstein discovered this idea in 1915, but it wasn't until 2 decades later, when he worked with a physicist named Nathan Rosen, that he realized his equations might contain more than gentle curves and predictable orbits. They might allow extreme distortions, folds so deep that space-time forms a tunnel, not a tunnel carved by matter, but one shaped by the fabric itself. Their insight began with a question: what lies at the center of a black hole? At the time, black holes were still theoretical. They emerged naturally from Einstein's field equations, but many physicists doubted that nature would ever create such a thing. Einstein himself was skeptical. Yet the mathematics insisted, if enough mass collapses into a small enough region, space-time curves infinitely, forming a singularity. But Einstein disliked singularities. They represented a place where the equations broke down, where space-time itself ceased to have meaning. To him, they felt like mathematical warnings, signs that something deeper waited beneath the surface. So he and Rosen sought a way to rewrite the geometry inside a black hole to avoid a singularity entirely. And what they found was surprising. They discovered that if you extend the geometry of a black hole carefully enough, the math creates a second region of space-time, a mirror universe on the other side of the horizon. A bridge connects the two, narrow at the center and widening as it reaches each universe. This was the first wormhole, the Einstein-Rosen bridge, hidden inside the structure of a black hole solution. Einstein didn't view this bridge as a passage anyone could travel through. To him, it existed only on paper, a quirk of the equations, a way to keep space-time smooth and avoid the unimaginable infinities of a singularity. But even as a mathematical artifact, it was something extraordinary. Two universes connected by a single throat of geometry. The bridge they described was not traversable. It pinched off too quickly. The slightest disturbance, the faintest attempt to enter it, would cause the throat to collapse. It was like trying to step onto a soap bubble. The moment you approach, it vanishes. And yet, the idea lingered. Einstein believed wormholes could exist because his own equations refused to forbid them. In physics, possibilities are born not from imagination, but from the consistency of mathematics. And the mathematics of general relativity allowed these bridges. They did not violate the laws of energy or momentum. They did not contradict causality. They simply required space-time to be curved in ways far more extreme than anything humanity had witnessed. But Einstein's belief was quiet, cautious, and grounded. He did not imagine wormholes as cosmic highways or shortcuts for travelers. Instead, he saw them as tools, mathematical structures that allowed him to think more clearly about the nature of space, time, and gravity. They were thought experiments in geometry, not predictions about engineering. Still, once the idea entered the scientific world, it grew into something larger. Over the decades, physicists began to explore the Einstein-Rosen bridge more deeply. They asked questions Einstein himself never pursued. Could the bridge remain open? Could something pass through? Could such a structure appear naturally in the universe, or even be created? The answers led to an entirely new field of gravitational physics. In the 1960s and 70s, as black hole research accelerated, scientists realized that Einstein's original bridge could be interpreted in a broader way, not only as a connection between two universes, but as a connection between distant regions of the same universe. The mathematics did not require separate cosmic domains, it only required steep curvature. This insight gave birth to the modern concept of a wormhole, a tunnel linking two distant places in space-time. Not a second universe, but this universe, folded back on itself. Why did Einstein's equations allow this? Because they treat space-time as continuous and dynamic. Distances are not fixed, boundaries are not absolute. Gravity can stretch or shrink the separation between points. Under extreme conditions, that separation can become so thin that the geometry connects. In Einstein's view, the universe is not a rigid stage. It is a living geometry, and living geometry can form surprising shapes. But the more physicists studied wormholes, the more they realized how fragile they are. A wormhole created by normal matter collapses instantly. Even light trying to pass through would tighten the throat and seal the passage. The Einstein-Rosen bridge is, by nature, a fleeting structure. Yet this fragility did not discourage researchers. Instead, it inspired one of the most intriguing discoveries of the last century: the idea of exotic matter. In the 1980s, physicists Michael Morris and Kip Thorne explored whether a wormhole could remain open if it were held apart by material with negative energy density. Not imaginary energy. Quantum theory already allowed tiny fluctuations of negative energy in special circumstances, but energy with gravitational repulsion. This was the first time wormholes were taken seriously as potential passages, not just mathematical curiosities. Thorne and his collaborators showed that Einstein's equations permitted stable wormholes, but only if the throat were lined with exotic matter. In other words, wormholes did not contradict general relativity. They required only that nature allow negative energy on macroscopic scales. Einstein never imagined this. He never sought traversable wormholes, but his belief in the underlying geometry laid the foundation for all later exploration. He understood that the universe is not built from objects and forces alone. It is built from structure, the curvature of space and time. And if space-time is allowed to curve in simple ways, it must also be allowed to curve in complex ones. The existence of one extreme object, the black hole, implies the possibility of another, the wormhole. The mathematics ties them together. Einstein believed wormholes could exist because his theory demanded that space-time be flexible enough to create them. He believed that geometry could take forms far beyond everyday experience. He understood that the laws of physics must be consistent not just with what we observe, but with every shape the equations permit. In that sense, his belief was not speculative. It was careful, respectful, mathematical. He trusted the framework he had built, and although Einstein never imagined humans traveling through wormholes, his work opened the door to a profound possibility: that the universe contains shortcuts not yet explored, paths hidden beneath the surface of space-time. As we continue our quiet journey, another question rises gently from this one. If geometry alone creates a wormhole, how does space-time bend sharply enough to form a tunnel at all? Now we drift into Part 3. Part 3. How does space-time bend enough to form a tunnel? Gravity is not a pull, it is the curvature of space-time itself. And when mass or energy grows intense enough, that curvature deepens into a well. Push the mathematics further, and the well becomes a throat, a narrow passage connecting two surfaces of the cosmic landscape. It is a shape born not from matter, but from geometry, straining under the weight of its own equations. To understand how space-time can bend enough to form a tunnel, we must first understand the calm machinery of curvature. In everyday life, gravity feels like a downward tug, a steady pull from the earth beneath your feet. But in Einstein's model, no pull exists. Instead, space-time itself is shaped, and everything, your body, the air you breathe, the orbiting moon, moves along the curves written by mass and energy. These curves are not metaphors. They are measurable paths, geodesics, etched into the fabric of the cosmos. Imagine space-time as a vast invisible surface. Place a heavy object on it, and the surface dips. Place something unimaginably heavy, like a star, and the dip becomes deeper. Replace the star with a collapsing core, and the dip steepens until it forms a point, a singularity, where the curvature is so extreme that the fabric can no longer be described in ordinary terms. This is the origin of a black hole. But hidden in the mathematics of these deep wells lies another possibility: the formation of a throat connecting one well to another. The pathway to such a tunnel begins with Einstein's field equations. the dense, elegant formulas that relate matter and energy to the curvature of spacetime. In these equations, the curvature does not depend only on mass, it also depends on pressure, momentum, and the flow of energy. Whenever these quantities reach extraordinary values, the fabric of spacetime reacts in extraordinary ways. Geometry twists, distances shift, time slows, and under some solutions, surfaces that were once separate can fold into contact. The key lies in understanding that spacetime is four-dimensional. We experience length, width, height, and time separately, but the universe does not. To spacetime, these directions are threads in one continuous weave. What looks impossible in 3 dimensions becomes natural in 4. Just as a 2-dimensional sheet can be bent through a 3rd dimension to allow 2 distant points to meet, spacetime can bend through its higher structure to create shortcuts. The bending required for a wormhole is not gentle. It is not like the curve of a planet's orbit or the sway of a galaxy's spiral arm. It is a violent distortion concentrated into a narrow region where geometry changes rapidly over extremely small distances. In this region, the difference between one point in spacetime and another contracts dramatically. The tunnel emerges from this contraction, a throat formed where distances are minimized by curvature instead of by travel. But what creates this extreme bending? In classical general relativity, only one ingredient is needed: stress energy. Mass contributes, pressure contributes, even light contributes, for light carries energy, and energy curves spacetime just as mass does. In fact, a sufficiently intense beam of light would warp spacetime along its path. But to form a wormhole throat, the bending must go beyond attraction. It must produce a funnel-like structure that narrows inward before opening outward again on the other side. This requires a very unusual distribution of stress energy, one that pushes outward against collapse. Ordinary matter cannot do this. Normal energy makes spacetime curve inward, deepening wells, tightening throats, encouraging collapse. To push outward, spacetime needs what physicists call negative energy density, something that stretches the fabric rather than compressing it. Negative energy reverses the usual curvature, creating bulges instead of dips, and when arranged in the right geometry, these bulges can hold a wormhole throat open. The existence of negative energy is not science fiction. In quantum field theory, the vacuum is not empty. It is a restless sea of fluctuations. Particles and antiparticles emerge and vanish, their energies briefly dipping below zero in ways consistent with the uncertainty principle. Phenomena such as the Casimir effect demonstrate that negative energy is real, though only in tiny, delicate amounts. 2 closely spaced metal plates experience an attractive force because the quantum fields between them have been squeezed into a state with lower energy than the surrounding vacuum, a state effectively requiring negative energy density. If spacetime can host negative energy on small scales, the idea arises: could a similar mechanism operate on larger scales, stabilizing a wormhole throat? The mathematics says yes, but nature has never revealed such a structure in the wild. To bend spacetime enough to form a tunnel, negative energy must be arranged in a way that continuously expands the throat against competing forces. Imagine holding open a heavy door in a hurricane. The pressure must not flicker. It must be constant, precise, and perfectly aligned. Exotic matter would provide this pressure, preventing the tunnel from collapsing inward faster than a traveler could enter it. This is where geometry becomes the central player. In Einstein's theory, curvature is not something added to spacetime. It is spacetime. The shape of the wormhole is written directly into the metric, the mathematical object that describes distances and times. When physicists solve the field equations, they are not manipulating objects inside space. They are changing space itself. A wormhole is therefore not a thing surrounded by spacetime. It is a reshaping of spacetime with no boundary between the structure and the world around it. One of the most illuminating ways to imagine this is through embedding diagrams, visualizations that show a slice of curved spacetime as if it were a 2-dimensional surface. When these diagrams depict a wormhole, they show 2 sheets connected by a throat, curved downward like a fountain or a catenary arch. The throat is the narrowest part, the region of greatest curvature. On either end, the sheets flatten into something more familiar, ordinary space where distances behave as expected. But the throat itself is pure geometry. No walls, no edges, just the fabric of space bending inward. Such extreme bending may seem exotic, but gravity has a long record of shaping the universe in unexpected ways. Neutron stars compress entire suns into spheres just 20 kilometers wide. Black holes fold spacetime until time itself slows to a stop at the event horizon. The early universe expanded faster than the speed of light during inflation. Once the cosmos demonstrated this flexibility, the idea that spacetime could form tunnels becomes less implausible. The fabric is capable of far more than the gentle arcs we see in planetary orbits. Yet, a wormhole's bending is unique. Most gravitational curvatures deepen into wells. A wormhole throat curves both inward and outward, depending on the direction from which you approach it. It is a saddle-shaped geometry. This dual curvature is the hallmark of negative energy. One side curves like the gravity of a star, the other curves like a region being, heat A, pushed apart. Spacetime bends enough to form a tunnel only when these two tendencies meet. Attraction shapes one side, repulsion shapes the other. Their balance creates the throat, a fragile equilibrium that ties distant regions into a single connected geometry. This is why wormholes are not simply holes in space. They are solutions, quiet answers written into the equations of relativity. They are the universe permitting a shape that normally remains hidden. And when that shape emerges on paper, another question naturally rises. What holds this fragile architecture open when everything in nature prefers collapse? Now we drift into Part 4. Part 4. Would time flow differently inside a wormhole? Every place in the universe has its own proper time, shaped by gravity and motion. Inside a wormhole, where space-time twists so sharply that normal surfaces fold onto themselves, time could run faster, slower, or in loops that defy intuition. Step into such a place, and your seconds may no longer match the universe you left behind. To understand why this happens, we have to begin with the quiet truth that time is not a universal rhythm. It has no single steady beat that echoes across the cosmos. Time flows differently near a black hole than it does in open space. It moves more slowly on the surface of Earth than it does aboard the International Space Station. Even the difference between your head and your feet is measurable with modern atomic clocks. The higher you stand, the faster you age. This is not philosophy. It is the direct consequence of Einstein's relativity. Time is woven into the curvature of space-time. Where gravity is stronger, time slows. Where gravity is weaker, time speeds up. Motion affects it too. The faster you travel relative to another observer, the more your seconds stretch. All of these effects are real, testable, and quietly at work in every moment of your life. Now imagine taking these same principles and pushing them into the most extreme geometry nature, or mathematics, allows. A wormhole. A place where space-time is bent not gently, but violently. A place where curves that normally describe orbits and gravitational wells become so sharp that two distant regions of the universe are brought into contact. Under such conditions, the normal flow of time doesn't merely change. It becomes part of the structure of the wormhole itself. Proper time, the time experienced by an object or traveler within a given region, would be stretched and bent just like the distances around it. The throat of a wormhole is not simply a spatial tunnel. It is a region where both the space and time components of spacetime curve in complicated interwoven patterns. This means that entering a wormhole does not just move you through space, it moves you into a new temporal landscape. In the simplest case, consider a wormhole that connects two distant points in normal space. If both mouths sit in regions with similar gravitational environments, then time might pass at nearly the same rate on each side. You could step in, cross through the throat, and emerge not only far away but almost synchronously in time. But wormholes do not need to be so gentle. One mouth could sit near a massive star deep within strong gravity. The other could drift quietly in interstellar space, far from any gravitational well. The difference in gravitational potential means that time at the two mouths passes at different rates. A clock placed near the star would tick more slowly. A clock placed far away would tick more quickly. If you travel through such a wormhole, you are not simply moving across distance. You are stepping between two different temporal realities. Imagine entering the throat from the region where gravity is weak. To you, only a short moment passes, but when you exit near the star, you emerge into a slower running time. From your perspective, the universe outside has been moving sluggishly. From the perspective of those near the star, you arrive surprisingly early. Reverse the journey, and the opposite occurs. Enter the wormhole near the star, travel through the throat, and emerge where gravity is weaker. Your seconds inside the tunnel may be the same, but the outside universe has aged more rapidly. You have stepped forward in time. This is the simplest version of time differentials in wormholes, and it already stretches intuition. But the geometry can become stranger still. If one mouth of a wormhole is accelerated, moved at high speed relative to the other, then motion, not gravity, becomes the source of temporal imbalance. Relativity tells us that a moving clock runs slow. So if one wormhole mouth takes a high-speed journey through space and then returns, its proper time will lag behind the other mouths. A traveler entering the older mouth and exiting through the younger one would emerge into the past relative to the outside world. In effect, they would step backward in time. This does not violate relativity. The geometry of spacetime allows it as long as the wormhole already exists and both mouths remain connected. But it does create causal paradoxes. A wormhole that allows two-way passage between different temporal regions becomes a time machine. And once a wormhole becomes a time machine, the equations of physics react sharply. Some solutions collapse, others destabilize. Many physicists believe that quantum effects, vacuum fluctuations amplified by the geometry, would flood the wormhole with energy and destroy it the moment a time loop is formed. This idea, often called the chronology protection conjecture, suggests that nature does not allow time machines to remain stable. Yet even if wormholes cannot enable time travel, they still alter the flow of time inside their structure. To understand why, imagine standing inside the throat of such a tunnel. The walls do not exist in the way we imagine walls. There is no physical boundary. Instead, the geometry around you pinches inward, narrowing the distance between two regions of spacetime. In this place, the usual markers of time lose clarity. A second measured inside the throat may not correspond to a second outside. Light itself, which normally travels along straight geodesics, twists along curved paths. A photon's journey might reflect a longer or shorter interval of time, depending on how the curvature shapes its route. Your perception inside the throat would be guided entirely by local time, your own proper time. You would not feel the difference. Just as astronauts in orbit do not feel their time running faster relative to Earth, a traveler inside a wormhole would feel normal. The strangeness emerges only when comparing your clock with a clock outside. If the wormhole were traversable, these differences could accumulate dramatically. You could leave one mouth at a particular moment, spend what feels like minutes inside the throat, and emerge hours, days, or years away, depending on how the two mouths sit within spacetime. Some models even allow multiple temporal gradients inside the same wormhole, time flowing more slowly near the throat, more quickly near the exit, or oscillating in patterns created by the shape of the geometry. The deeper physics behind this lies in the metric tensor, the mathematical object that describes distances and durations in spacetime. Inside a wormhole, the metric changes rapidly. Time dilation and spatial distortion become inseparable. They are not two separate effects, but one unified deformation. The geometry dictates how fast clocks tick and how far distances extend. A wormhole is, in this sense, a machine not only of travel, but of altered temporal experience. And yet, for all these extraordinary effects, your journey might feel peaceful, smooth, quiet. Just as a falling object follows the natural curve of spacetime, you would drift through the throat along a geodesic, feeling weightless and calm. The universe would be bending around you, carrying you forward through both space and time. The transformation would be external, not internal. Your heartbeat, your breath, your perception of seconds would remain unchanged. Only when you emerge would you see what space-time has done. Your watch would tick normally. The stars around you would not. A friend waiting outside might be older or younger than expected. Light traveling between the two mouths might arrive early or late. The universe would reveal that time inside the wormhole had flowed along a different path. And so the answer becomes clear. Time inside a wormhole does not simply run differently. It becomes part of the geometry that defines the tunnel. It is woven into the throat, stretched across the curvature, shaped by the positions and motions of the mouths. As we continue our quiet journey, one question naturally arises. What substance, if any, could support such a fragile structure through which both time and space are bent so profoundly? Now, we drift into Part 5. Part 5. Why do wormholes require exotic matter? To hold a wormhole open, space-time needs support, something that pushes outward against collapse. Ordinary matter cannot do this. Its gravity only tightens the throat. But exotic matter, with negative energy density, would do the opposite. It would push space apart instead of drawing it together, creating an anti-gravity scaffold that could keep the passage stable. This requirement sounds strange at first, almost unnatural, as if the universe is demanding something it rarely provides. And yet it follows directly from Einstein's equations. Every curvature in spacetime depends on the distribution of matter and energy. When matter pulls inward, spacetime curves inward. When energy flows outward, spacetime reacts accordingly. A wormhole demands an outward curvature, a throat that refuses to collapse, a bridge that remains open even as gravity tries to pinch it shut. To achieve such a shape, spacetime needs a source of support that behaves differently from everything we know in everyday life. Ordinary matter simply cannot supply this. Place normal matter near a wormhole throat and its gravitational pull will increase the curvature, narrowing the passage until it closes. Even light contributes to this collapse. Light carries energy and momentum, and these quantities increase curvature just as mass does. If even a single photon tries to pass through, the throat becomes tighter. The wormhole shrinks. Collapse follows. This is why the Einstein-Rosen bridge, the earliest wormhole solution, is not traversable. It exists only for an instant. The moment anything touches it, it seals itself. To transform such a fragile structure into something stable, the geometry needs help. It needs a material with negative energy density, something that curves spacetime outward, pushing it open rather than pulling it inward. Negative energy is not the same as the absence of energy. It is a real, physical quantity predicted by quantum field theory. If you picture the vacuum as empty, relativity breaks. The vacuum is not empty. It is alive with fluctuations, particles appearing and vanishing in fractions of a second. In this restless sea, the energy is not constant. It can dip below zero in tiny, fleeting pockets. These pockets obey the laws of physics. They appear naturally. They can even be seen in experiments. One such experiment is the Casimir effect. When two reflective metal plates are placed extremely close together, the quantum fields between them are squeezed into a restricted configuration. Fewer wavelengths fit between the plates than outside them. The energy density in this inner region becomes lower than the energy density outside, effectively a negative relative energy. This difference pulls the plates together with a measurable force. That force is small, almost imperceptible, but it proves something fundamental. The universe allows negative energy. It permits states where the vacuum's energy dips below its usual level. Negative energy is not imaginary. It is part of the physical world. The problem is scale. The Casimir effect produces negative energy in amounts far too small to support anything larger than the tiniest gap between plates, let alone a stable wormhole throat kilometers or light years wide. But the mathematics remains clear. If one could obtain enough negative energy and shape it into the right configuration, spacetime would respond. It would hold the throat open. In the 1980s, physicists Michael Morris and Kip Thorne explored this idea deeply. They asked, if exotic matter existed in useful quantities, What would it allow? Their answer was profound. A wormhole supported by negative energy could remain stable indefinitely. It could resist gravitational collapse. It could be traversed. A traveler entering the throat would not be crushed. Light could pass through without tightening the curve to the breaking point. The geometry would remain open like a tunnel whose walls push outward. The exotic matter would not be a wall. It would be a region of space-time itself, a distribution of negative pressure that literally stretches the geometry outward. Physicists describe it as tension rather than mass. Instead of pulling inward, as every object with positive energy does, exotic matter creates a local pushing effect. This outward push is essential because wormholes are naturally unstable. Without exotic matter, the infinitesimal disturbances caused by even a passing photon would collapse them. With exotic matter, the throat becomes a balanced structure: inward curvature from normal gravity, outward curvature from negative energy. In this equilibrium, a tunnel emerges. But exotic matter introduces its own mysteries. Negative energy violates what is called the weak energy condition, a principle of physics stating that energy density as measured by any observer must be non-negative. Exotic matter breaks this rule, and while quantum field theory does allow small violations over tiny regions and brief durations, it does not readily allow large, persistent violations. A wormhole throat would require exactly that: negative energy sustained over macroscopic distances and times. Not a flicker, not a fluctuation, a stable scaffold. Does the universe produce such scaffolds naturally? As far as we know, no. We have never observed large-scale negative energy in cosmic structures. We have seen dark energy, which drives the accelerated expansion of the universe. But dark energy is not the same as the negative energy needed for wormholes. Dark energy has positive energy density. It simply has negative pressure. It stretches the universe on vast scales, but it does not create local regions of negative energy capable of stabilizing a throat. Even so, the possibility remains open. Nothing in the laws of relativity forbids negative energy. Quantum mechanics endorses it on small scales. This is why wormholes are not dismissed as fantasy. They are permitted mathematically. They simply require conditions the universe does not seem eager to generate. If someday a civilization were advanced enough to engineer such conditions, they would have to manipulate quantum fields precisely. They would need to extract negative energy, amplify it, and stabilize it. They might rely on advanced forms of vacuum engineering, reshaping the fluctuations of the quantum field, squeezing space itself until negative energy densities grow large. They might create artificial boundaries, similar to the Casimir plates but on astronomical scales. Or they might draw from physics we have not yet discovered. In such a future, a wormhole would be less of a structure and more of a maintained state. Exotic matter would not be bricks holding up a tunnel. It would be the pressure distribution keeping space-time in a particular shape. Like wind holding a sail or tension holding a suspension bridge, exotic matter would maintain the geometry against collapse. The idea is subtle and deeply beautiful. It suggests that wormholes are not holes carved through space, but shapes sustained by energy and curvature. They exist only while their delicate balance is preserved. With enough exotic matter, this balance could be maintained. Without it, the throat closes instantly. In this sense, exotic matter is not an extra ingredient added to a wormhole. It is the defining ingredient. Without it, the tunnel is not a tunnel at all. With it, space-time becomes something new, something open. And yet, even if exotic matter can exist in large quantities, another question arises. What happens the moment a traveler enters the throat? Does the structure remain intact? Does the negative energy hold? Or does the act of crossing the boundary change the geometry enough to risk collapse? These questions lead us deeper into the fragile nature of the passage itself. And so, as our journey continues, another quiet question emerges. Even if a wormhole can be held open, would entering it cause the tunnel to shut? Now we drift into Part 6. Part 6. Would a wormhole collapse the moment you enter it? Most wormholes predicted by Einstein's equations pinch off instantly. They are like bubbles appearing and vanishing, too brief for anything to pass through. The moment a traveler approaches, their mass strengthens gravity and the throat snaps shut. To survive such a crossing, the structure would require an outward pressure stronger than collapse itself, a physics we do not yet command. To understand why this collapse happens, we have to start with the quiet truth of gravity's nature. Gravity is not an external force tugging at us, it is the shape of space-time itself. And space-time follows simple instincts. It tries to minimize tension, it tries to smooth distortions. Any sharp curvature, any strange geometry is temporary unless supported by the right balance of energy. Wormholes, more than any other structure in general relativity, push space-time into one of its most extreme shapes. They ask the fabric of the universe to maintain a narrow throat linking two wide openings across vast distances. Without support, the fabric recoils. This recoil is instantaneous in most solutions. A wormhole forms, flickers, and disappears before even light can traverse it. Physicists call these non-traversable wormholes. The collapse happens because the inward pull of gravity around the throat is far stronger than anything that would hold it open. The geometry caves in, sealing the passage before an object, no matter how small, could cross. Even the attempt to enter accelerates the collapse. A traveler carries mass, and mass deepens curvature. The throat becomes narrower simply because the approaching traveler adds gravitational influence. It is like trying to step onto a fragile ring of soap film. The moment your fingertip touches the surface, the film retracts into a single glistening droplet. A wormhole throat behaves the same way. Geometry cannot withstand the disturbance. The mathematics behind this is precise. When you insert mass into a wormhole throat, the equations show curvature rising sharply. The inward pull exceeds the outward push. The throat's radius decreases. As the radius approaches zero, the wormhole matches the geometry of a black hole. An event horizon forms, the passage closes, and anything inside becomes trapped. The traversable path becomes a one-way fall. But collapse is not a failure of the idea of wormholes. It is simply the natural response of space-time when negative energy is absent. To keep a wormhole open requires a substance capable of counteracting the inward pull, exotic matter with negative energy density. Without it, stability is impossible. With it, stability becomes fragile but achievable. Imagine the throat of a wormhole as a delicate archway. Gravity acts like a weight pushing down, trying to flatten the curve. Exotic matter acts like an invisible support beam, pushing outward against collapse. If the support beam is strong enough, the arch stands. If the beam weakens, even slightly, the arch folds inward. This analogy helps us understand how sensitive wormholes are. For even a tiny object to pass through, the negative energy holding the throat open must be strong enough to resist the mass's gravitational contribution. Not just slightly stronger, significantly stronger. The geometry must remain balanced not only in empty space, but under the stress of a traveler moving through it. The question then becomes, could any realistic amount of exotic matter maintain this balance? Current physics does not yet provide an answer. Negative energy exists only in quantum fluctuations, and these fluctuations are small, brief, and difficult to harness. They appear and vanish like sparks in the vacuum. But a stable wormhole would require a sustained region of negative energy dense enough to support a tunnel large enough for matter to pass through. It would require shaping the quantum vacuum into a persistent configuration, a feat far beyond our engineering capabilities. Even if such exotic matter could be generated, the wormhole's stability would remain precarious. Consider the traveler's motion. As they accelerate into the throat, their momentum adds energy to the curvature. As they carry charge or angular momentum, they modify the local geometry. Even their thermal radiation contributes to stress energy. Any fluctuation might destabilize the throat. A slight imbalance could cause the wormhole to pinch shut around the traveler, trapping them inside a region of extreme curvature. Physicists describe this using the concept of tidal forces. In a stable wormhole, tidal stresses must be low enough to avoid stretching or crushing objects. But in a wormhole on the edge of collapse, tidal forces rise rapidly. A traveler might feel nothing at first, a sense of weightlessness, perhaps even calm. But at the throat's center, the forces could spike suddenly, tearing apart anything in their path. The collapse would be silent, swift, unstoppable. Yet the story does not end in collapse. Because even as most wormholes fail, the mathematics also reveals a path toward stability. If negative energy is arranged in the right configuration, and if the geometry is tuned precisely, the wormhole can resist collapse even under stress. The throat widens slightly as a traveler approaches, counteracting the added curvature. The geometry adjusts itself, absorbing the disturbance like a self-regulating bridge. This idea leads to an astonishing possibility, a wormhole that senses its own destabilization and strengthens in response. Not because it is alive, but because the distribution of exotic matter reacts to changes in curvature. Scientists call this a self-consistent geometry, a configuration that remains stable under small perturbations. But even a self-consistent wormhole would have limits. Too much mass, too much energy, too rapid an acceleration, and the throat would still collapse. Traversing a wormhole would require gentle motion, careful alignment, and a precise understanding of how the geometry behaves under stress. Entering a wormhole would be more like gliding into a tranquil current than stepping through a doorway. Too abrupt a motion, too strong a disruption, and the current tears apart. Even if a wormhole could remain open during entry, another question emerges. What happens to the exotic matter itself? Negative energy is notoriously unstable. If disturbed, it could disperse. If heated, it could collapse. If interacted with in the wrong way, it could revert to ordinary energy, losing its outward push. The act of passing through might itself consume or destabilize the exotic matter, weakening the throat and initiating collapse even after the traveler has entered. This highlights the fragility of the entire concept. A wormhole is not a tunnel carved through stone. It is a dynamic shape in spacetime held open by a delicate balance of forces. Disturb it, and the shape returns to what spacetime prefers: smoothness, symmetry, simplicity. A wormhole is an interruption of simplicity. Nature tends to erase such interruptions the moment they appear, and yet the possibility remains. If exotic matter can be stabilized, if curvature can be shaped, if quantum fields can be engineered, then the collapse might be prevented. A wormhole could be crossed, a traveler could enter the throat, drift into its geometry, and emerge on the other side before nature has time to reclaim the structure. But that possibility raises the next question in this quiet exploration. Even if a wormhole survives your entry, could it connect not only distant places, but different moments in time? Now we drift into Part 7. Part 7. Could wormholes connect different times, not just places? In spacetime, distance and duration are woven into the same fabric. Bend one sharply enough, and the other bends too. A traversable wormhole, if one could exist, might align two mouths at different temporal states. Enter one end, and you might emerge not only far away, but decades earlier or later. A door not only across the cosmos, but across the calendar. To understand how this could happen, we have to step back and remember what time truly is. We often imagine it as a universal river, a steady flow that carries everything forward at the same rate, but the universe does not experience time this way. In Einstein's relativity, time is local, it is personal, it is shaped by gravity, shaped by motion, shaped by the curvature of the universe itself. Your seconds are not identical to the seconds of someone moving quickly or someone standing deeper inside a gravitational well. Time becomes elastic. Clocks on satellites orbiting Earth tick faster than clocks on the ground. Atomic clocks raised a few centimeters experience time differently from those left below. Even the expansion of the universe stretches time in distant galaxies in subtle but measurable ways. Everywhere you look, the cosmos is telling us the same quiet truth. There is no single universal now. And once you accept that, an even stranger truth follows. If a wormhole connects two regions of spacetime and those regions experience time differently, then the wormhole itself becomes a bridge not only between locations, but between temporal states. Enter one mouth and you emerge where time flows at a different rhythm. The geometry does not simply take you across distance, it takes you into another moment. This idea begins with a simple principle. If two clocks tick at different rates, and if a wormhole links the regions where those clocks reside, the wormhole becomes a shortcut that bypasses the difference. That difference becomes the time shift between the wormhole mouths. Imagine two mouths of a wormhole floating in space, initially side by side. Time passes normally for both. Their internal clocks run in sync. Now, imagine moving one mouth. If you accelerate one mouth to a significant fraction of the speed of light, carry it through space and bring it back, its internal time will lag behind the stationary mouth. This is special relativity. Moving clocks tick more slowly. Or imagine lowering one mouth deep into a gravitational well, near a massive star, for instance. Time there runs slower. The other mouth, far from the star, experiences time more quickly. This is general relativity. Gravity slows time. In either case, the wormhole throat does not break. It remains a stable geometric link, at least in theory. So the two mouths, now experiencing different rates of time flow, remain connected by a single internal passage. From the outside, time differs. Inside the wormhole, time remains smooth. This is the key. A traveler entering the accelerated mouth could step into the throat and exit the stationary mouth, arriving in that region's future. Reverse the direction, and the traveler emerges into its past. The wormhole becomes a bridge between two moments. Not because anything mystical has happened, but because relativity has quietly reshaped the flow of time on each end. This concept is unsettling, but it arises directly from Einstein's equations. In fact, the math is remarkably clear. Any traversable wormhole whose two mouths undergo different histories in spacetime will connect different temporal regions. This does not automatically allow paradoxes. It does not guarantee the ability to change history. The laws of physics may enforce deeper protections, but the geometry itself allows the possibility. To understand how such a structure might feel from the inside, imagine entering the wormhole at the younger mouth. Your journey through the throat is smooth, weightless, almost dreamlike. Proper time, the time you yourself measure, passes normally. Seconds feel like seconds. Breathing feels like breathing. But when you step out on the other side, the universe around you is older. Stars have shifted, clocks have advanced, events have unfolded without you. You have walked into the future simply by following the natural curvature inside the throat. Reverse the process and the effect becomes even stranger. Enter the older mouth and emerge where time has passed more slowly. You arrive into a region that has not yet aged as much as the one you left. To the outside world, you have stepped backward in time. It is important to emphasize that none of this violates relativity. Wormholes do not break physics, they simply exploit its geometry. The real challenge lies not in the mathematics, but in stability. A wormhole behaving as a time machine would produce enormous strains on its structure. Quantum fluctuations might amplify. Negative energy distributions might destabilize. Radiation could accumulate inside the throat. These effects could collapse the wormhole the moment a closed time-like curve, an actual loop in time, begins to form. This idea is known as the chronology protection conjecture, coined by Stephen Hawking. It suggests that nature prohibits stable time machines because the energy required to maintain them would diverge to infinity the moment paradoxes become possible. In other words, wormholes might resist being used for time travel by collapsing whenever the geometry threatens causality. But even if collapse prevents actual time loops, wormholes could still connect different temporal states without forming paradoxes. A wormhole mouth that is aged differently from its partner is simply an asymmetric passage. It creates a time shift, not a time loop. Imagine it as two doors connected by a hallway. One door has experienced 10 years, the other only one. Walking through the hallway does not force the world into a paradox. It merely places you in a region of space-time with a different temporal history. This is not time travel in the fictional sense. You cannot jump centuries into the past and meet yourself. You cannot alter events already set. You can only move between different segments of a timeline that already exists, each shaped by motion and gravity. Still, the implications are profound. A wormhole could allow civilizations to synchronize across vast cosmic distances. It could allow communication across long stretches of time. It could let explorers leave one region of space and return to another at a moment long before or long after they left. It could make the flow of time itself a navigable landscape, but these possibilities remain theoretical, fragile, and deeply tied to physics we have not mastered. The exotic matter required to hold the throat open, the precision needed to maintain stability under acceleration, the delicate control of curvature. All of these lie far beyond our capabilities, yet the mathematics continues to whisper, the door is not locked. The universe does not forbid such a bridge. It simply demands conditions that nature rarely provides. And this leads to another quiet question. If wormholes can connect times as well as places, what would you actually see as you approach one? How would the universe appear when space and time fold together? Now we drift into Part 8. Part 8. What would you see if you approached a wormhole? You would not see a tunnel. You would see distortion, light bending around an invisible throat, stars stretched into rings, colors twisted by extreme gravity. The wormhole itself would be dark at its center, surrounded by a shimmering halo where the universe curves so sharply that photons are forced into spirals. You would approach not an opening, but a quiet gravitational whirlpool. To imagine this sight fully, you have to set aside familiar instincts. In everyday life, objects appear where they physically are. Light travels in straight lines, distances behave predictably, but near a wormhole, none of these assumptions hold. Gravity does not just pull, it warps the path of light itself, bending every ray into curves, arcs, and loops. You would not see the wormhole as an object. You would see the effect it has on everything around it. The first sign would be subtle. Stars in the background would shift slightly, as though a lens were passing in front of your vision. This phenomenon, gravitational lensing, is well known around massive objects like galaxies and black holes, but a wormhole would produce a far more extreme version. Its lensing would not simply magnify distant light, it would twist and smear it. Points of light would elongate into arcs, constellations would stretch and ripple. The sky itself would seem to bend toward the center of your field of view. As you draw closer, the distortion would grow stronger. Light paths that would normally carry information directly to your eye would curve instead, diverted by the sharp geometry around the wormhole throat. Some photons would loop entirely around the throat one or more times before reaching you. This creates a phenomenon known as a photon ring, an intense, thin band of light surrounding the dark center. Astronomers have recently imaged such rings around black holes. A wormhole would produce something similar, though not identical. The shape of the ring would depend on the precise geometry of the throat, wider, narrower, more circular, or more elliptical depending on the wormhole's structure. The dark region in the center would not be a hole in the sense of an absence. It would be a zone where light is redirected so sharply that almost none of it reaches your eyes. It is not darkness from emptiness, but darkness from diversion. Light is not swallowed the way it is by a black hole. Instead, it is sent elsewhere, slipping through the throat or circling endlessly within the curvature. Around this darkness, the shimmering halo appears. This halo is caused by photons approaching the wormhole at various angles. Some skim close to the throat and are bent into spirals. Some loop once before escaping. Some loop multiple times, creating delicate concentric rings of diminishing brightness. These rings are not bright like stars. They are subtle, faint, like reflections on the surface of deep water. They shimmer not because they move, but because the geometry makes your perspective shift with every moment you come closer. Colors would stretch too. The gravitational field near a wormhole can redshift or blueshift light, depending on its motion and the observer's position. Growing closer, you might see stars near the edges of the halo appear slightly bluer, their wavelengths compressed by the intense curvature. Deeper into the throat's shadow, colors might fade toward red, their wavelengths stretched as they climb out of the geometry's pull. In some directions, the effect would be so strong that stars could vanish entirely, their light redirected away from your line of sight. If the wormhole were rotating, a possibility allowed by certain solutions of general relativity, the visual effects would gain a quiet swirl. Frame dragging, the twisting of spacetime by rotating mass or energy, would subtly twist the patterns of lensing. The halo would appear slightly asymmetric. Light would flow in gentle arcs, curves leaning more strongly to one side, like water circling a drain. But again, this swirl would not be fast or violent. It would be patient, steady, almost delicate in its motion. The closer you drift toward the throat, the more dramatic the distortion becomes. Space around you would seem to bend inward. Background stars would elongate into thin streaks, as though the universe were being drawn toward the center. The wormhole would behave like a magnifying glass for distant galaxies, stretching their light into luminous threads. Some threads might cross or overlap, forming bright knots where lensing gathers photons along similar paths. If the wormhole connects distant locations in the universe, you might even catch hints of the other side. Not a clear view, never a clear view, but a faint ghostly pattern of light inconsistent with the stars behind you. A distant cluster that should not be visible. A patch of sky whose age or distribution of galaxies does not match your current region. These would appear subtly at first, then more distinctly in the final moments before reaching the throat. But even then, you would not see a tunnel. What waits inside the throat is not a physical cavity lined with walls. It is a region of space-time where distances contract and paths converge. Vision fails because light behaves differently inside the geometry. What you perceive as darkness might be brightness hidden from your direction. What looks like shimmering chaos might be a stable, predictable pattern of geodesics. The natural paths light takes through curved space. Your senses were never built to interpret such geometry. They evolved for flat landscapes, slow motions, gentle curves. A wormhole violates those expectations. It bends the backdrop of the cosmos into something unfamiliar. And as you approach, you would feel less like you are closing in on an object and more like you are entering a region of altered perspective. The transition into the throat itself would be silent. No wind, no heat, no sudden jolt. The change would be perceived only through vision, distortions growing stronger, shapes becoming surreal, until the curvature overwhelms your ability to interpret. The halo would expand across your field of view. The center would swallow more of the stars behind it. The universe would appear to narrow around you. And then, something subtle happens. The distortions cease to resemble distortions because the geometry becomes your new normal. Light enters from directions your mind cannot map. Stars seem to gather in impossible clusters. In this zone, the familiar idea of forward loses meaning. You drift through curves, not straight lines. What you see becomes a blend of the space you came from and the space you are headed toward. Two regions of the universe overlapping faintly in your perception. In this sense, approaching a wormhole is less like approaching a door and more like approaching a horizon between two geometries. The light that reaches your eyes comes from multiple directions of space-time at once. The halo becomes a guide, tracing the transition between the outside universe and the throat. If you were to turn back at the last moment, the distortions would unwind. The sky would slowly regain its familiar shape. The arcs would collapse back into stars. Colors would return to their natural wavelengths. It would feel as though the universe exhaled. But if you continue inward, crossing the invisible boundary, your perspective shifts entirely. What you see becomes governed by the interior geometry, not the exterior lensing. The throat surrounds you, and the distortions of the outside world vanish behind you. And as you drift deeper, one quiet question follows naturally. What happens to light itself once it enters the throat? Does it escape? Does it spiral endlessly? Does it emerge unchanged on the other side? Now, we drift into Part 9. Part 9. What happens to light inside a wormhole? Light follows the shortest path through spacetime, even when that path is not straight. Inside a wormhole, those paths twist inward, guiding photons through the throat. But the geometry is unstable. Some rays may escape, others may loop indefinitely, and some may fall into regions where spacetime folds so tightly that motion itself becomes impossible. To understand what this means, we must remember what light truly is in Einstein's universe. It is not a particle traveling through space the way a stone travels through air. It is the motion of spacetime's own electromagnetic fields, and it does not choose its direction, it obeys the curvature beneath it. When gravity bends spacetime, light bends with it. When geometry stretches or twists, light follows those shapes exactly. A wormhole is one of the most extreme shapes that spacetime can adopt. It is not a simple curve like the orbit of a planet or the gravitational well around a star. It is a region where the geometry folds inward, forms a throat, and reconnects with itself somewhere else. In everyday life, the shortest distance between 2 points is a straight line. Inside a wormhole, the shortest distance may pass through a tunnel. Light, always faithful to geometry, behaves accordingly. Imagine entering the region around a wormhole mouth. Even before reaching the throat, photons begin to curve. The curvature is not gentle, it is sharp, like the slope of a deep well. Rays that would normally travel past you suddenly veer inward. Rays from behind you may loop around and re-enter your field of view. Distant starlight stretches into arcs and halos. The behavior is similar to the lensing around a black hole, but subtly different, because while a black hole captures all light that crosses its horizon, a wormhole redirects some of it into the throat. Now, consider the moment when a photon approaches the throat itself. In the mathematics of wormholes, the throat is a region where distances contract dramatically. A photon falling along a geodesic, a natural path in this curved space, may find itself funneled inward. Some of these geodesics lead directly through the throat. These photons pass cleanly from one side of the wormhole to the other, emerging in a different region of the universe as if they had traveled faster than light through normal space. They do not violate relativity, they simply follow a shorter path through a different geometry. But not all photons pass straight through. The geometry is delicate. It varies depending on the mass distribution, the degree of exotic matter supporting the throat, and the wormhole's rotation. Some light rays approach at angles that guide them into orbit around the throat. These orbits can be stable or unstable depending on the shape of the wormhole. If the geometry is smooth and symmetric, a photon may loop around the throat again and again, tracing a perfect circle of light. This creates the bright, thin rings often described in visual models of wormholes, rings formed by photons orbiting just outside the throat, caught between escape and capture. Other rays enter more complex trajectories. They may spiral inward, looping tighter and tighter until they pass through the throat or fall into regions where escape is impossible. In highly curved geometries, these spirals can become chaotic. Tiny differences in angle or position lead to radically different outcomes. One photon escapes after a single loop. Another loops indefinitely. A third crosses the throat. A fourth collapses into a region where geodesics converge so tightly that motion becomes trapped. These trapped regions are not singularities. Wormholes, unlike black holes, do not require infinite curvature at their centers, but they can host zones where the curvature becomes extreme enough to act as a barrier. Light entering these zones slows, not in its speed, which always remains constant relative to local spacetime, but in its progress along wider coordinates. The path ahead narrows. Geodesics converge. The photon is not destroyed, but confined. Its existence becomes tied to the geometry of the throat. This leads to a remarkable idea. Inside a wormhole, light can become part of the structure. Orbiting photons trace out rings that reveal the wormhole's shape. Spiraling photons contribute to the energy distribution. Trapped photons remain suspended in the geometry, their trajectories frozen by curvature. Light, which normally illuminates, becomes a quiet prisoner of spacetime's architecture. But light can do something even stranger. It can reflect the wormhole's temporal structure. If the two mouths of a wormhole experience time differently, the timing of photon arrivals can become mismatched. Imagine shining a beam of light into one mouth. If the other mouth is in the future relative to the first, the beam may emerge before the instant it was emitted, according to an outside observer. Conversely, if the second mouth is in the past, the beam may emerge into a region that has not yet aged as much as the region where it originated. This does not create paradoxes by itself. It simply reflects the differences in proper time between the mouths, but it highlights how profoundly the geometry shapes not just space, but time. Now, consider a rotating wormhole. Rotation introduces frame dragging, the twisting of spacetime caused by angular momentum. In such a wormhole, light does not simply curve radially, it also twists. The geodesics spiral more intensely. Photon orbits lean to one side, rings become asymmetric. Light entering one side of the throat may be swept along a curved path that traces a slow whirl within the geometry before escaping. The effect is subtle but beautiful. It is as if the very act of rotation paints patterns onto the paths that photons follow. Stillness becomes swirl, symmetry becomes flow. The fate of light depends on the stability of the wormhole itself. If the wormhole is unstable, even slightly, the geometry may fluctuate as photons travel through it. A photon moving through a narrowing throat may experience blue shift, its wavelength squeezing shorter as it falls deeper into curvature. A photon moving into a widening region may be redshifted, its wavelength stretching longer as the curvature weakens. In extreme cases, these shifts become infinite. Light entering a collapsing throat may be stretched until its wavelength becomes unimaginably long, rendering it undetectable. Light entering an expanding throat may be crushed into energy so intense that it no longer resembles ordinary radiation. Through all of this complexity, one theme remains constant. Light reveals the geometry. If you could view the wormhole not with human eyes, but with perfect detectors capable of tracking individual photons, you would see the shape of spacetime itself. Every ring, every arc, every distortion would be a map of the curvature. Light does not lie. It follows the true contours of the universe, tracing them like ink flowing across invisible paper. This makes wormholes simultaneously mysterious and revealing. Their interiors are inaccessible to ordinary intuition, yet they advertise their shapes through the behavior of light. A wormhole might be invisible as an object, but it cannot hide its gravitational influence on photons. Some scientists have proposed that if wormholes exist naturally in the universe, we might detect them not by seeing the throat itself, but by observing the unique patterns of lensing they produce. A wormhole connecting two regions of the cosmos might cause repeated images of distant objects, ghostly duplicates appearing in unexpected places, or it might distort the cosmic microwave background in ways unlike any galaxy or black hole. Light would betray the tunnel even if the tunnel remains unseen. And as we follow light deeper and deeper into the wormhole's throat, one quiet question emerges. If the universe resists forming such tunnels naturally, why do they appear so rarely? What cosmic forces prevent these extraordinary structures from becoming common? Now we drift into Part 10. Part 10. Why are wormholes so difficult to form naturally? The universe prefers stability. Stars collapse into black holes because it is the simplest arrangement for enormous mass. Wormholes, by contrast, require balance between inward and outward pressures that nature rarely provides. The equations allow them, but the cosmos seems reluctant to construct them, like arches in stone before mortar was invented. To understand why wormholes resist forming naturally, we have to look at the fundamental instincts of space-time. In Einstein's universe, curvature arises from mass and energy. Wherever matter gathers, space-time curves inward. This inward curvature is the universe's most natural motion. Clouds collapse into stars, stars collapse into neutron cores, and collapsing cores form black holes. Nature follows the path of least resistance, moving from diffuse states into tighter, more compact configurations. A wormhole is the opposite of this instinct. It requires the fabric of space-time to curve outward in some regions, even as it curves inward in others. It demands a throat supported by negative pressure, an outward push that fights collapse. But the cosmos, as we observe it, rarely offers such outward forces in the concentrated form a wormhole needs. Negative energy exists in theory and in tiny quantum fluctuations, but not in sustained macroscopic quantities. The vacuum fluctuates, but it does not build tunnels. Yet wormholes do appear in Einstein's equations. They emerge as mathematical solutions, just as black holes do. The difference is that black holes correspond to physical processes we know, the collapse of massive stars. while wormholes correspond to no known cosmic mechanism. The universe can form a black hole by letting gravity run its course. It would need something far more exotic to form a wormhole. The first barrier is symmetry. Wormholes require highly specific configurations of curvature. If you imagine the fabric of spacetime as a sheet, black holes are easy creases. Gravity pulls the sheet downward. Wormholes require two such depressions connected perfectly at their narrowest points, forming a smooth bridge. Nature does not naturally fold this sheet into such a structure. When mass collapses, it sinks. It does not tunnel. Even if two collapsing regions existed near each other, their inward curvatures would not align into a stable throat. They would simply form two separate black holes. If those black holes orbit one another, they merge rather than connect. If they collide, they generate gravitational waves and produce a larger black hole. The geometry smooths out. The bridge never forms. The second barrier is energy conditions. Wormholes require violations of classical energy assumptions, specifically the weak energy condition, which asserts that energy density must be non-negative for any observer. This holds true for all known forms of matter and radiation. Even the densest stars obey it. The only known violations occur in the quantum realm, in short-lived microscopic pockets where fluctuations dip below zero. These fluctuations are too small to shape the geometry on astrophysical scales. They flicker for trillionths of a second. To build a wormhole, nature would need to stretch and stabilize such fluctuations into extended regions large enough to support a throat that spans kilometers or light years. Nothing in the cosmos seems capable of doing this spontaneously. The third barrier is instability. Even if a wormhole formed briefly through some exotic process, perhaps during the extreme conditions of the early universe, it would collapse almost instantly. Without sustained negative energy to counterbalance the inward pull of gravity, the throat pinches shut faster than light can cross it. In simulations, this collapse occurs so quickly that the wormhole behaves like a flicker, a transient feature of the gravitational landscape, not a stable passage. Some physicists have speculated that the universe might have produced microscopic wormholes during the inflationary epoch, the moment after the Big Bang, when space expanded faster than the speed of light. This period was chaotic, energetic, and filled with quantum fluctuations. The geometry may have briefly contorted into strange configurations, including wormhole-like structures. But if they formed at all, they would have been incredibly tiny, smaller than atoms, smaller than protons, perhaps even at the Planck scale. Such microscopic wormholes would appear and vanish within unimaginably short timescales, far too brief for anything to pass through. And as the universe expanded and cooled, they would collapse or evaporate. The large-scale stability required for a traversable wormhole simply was not present. The fourth barrier is entropy. Nature tends toward disorder, and wormholes demand order. They require symmetry, alignment, precise curvature. They cannot tolerate uneven distributions of mass or radiation. If a wormhole mouth encounters too much normal matter, the added curvature collapses the throat. If it absorbs even small amounts of thermal energy, its structure destabilizes. In a universe filled with particles, radiation, and fluctuations, maintaining such perfect balance is difficult. Nature does not like finely tuned systems. It prefers robust, resilient configurations like black holes and neutron stars. Another obstacle is cosmic expansion. The metric expansion of space stretches distances between galaxies. It also dilutes fluctuations in energy density, making it harder for regions of spacetime to sustain the gradients necessary for wormholes. Inflation may have created extreme distortions, but it also erased them by expanding them faster than they could stabilize. The universe today is far calmer, far smoother, far less capable of producing the conditions that wormholes require. Even the known forms of cosmic repulsion, such as dark energy, do not help. Dark energy pushes the universe apart, but it is uniform, spread thinly across all of space. It cannot concentrate into the local, intense negative pressure needed to hold open a throat. Dark energy is like a gentle wind filling all of space-time equally, not a focused beam of force that could sustain a tunnel. In this sense, wormholes sit in the liminal space between mathematical possibility and physical improbability. The equations make room for them. They do not forbid tunnels any more than they forbid flat planes or curved spheres. But the universe, as far as we can observe, is not inclined to build these tunnels. It chooses simplicity over complexity, collapse over balance. This does not mean wormholes could never exist naturally. It simply means that if they do, they are extraordinarily rare. They might require conditions that occur only in the earliest instance after the Big Bang. Or they might require forms of matter and energy we have not yet discovered. Perhaps the universe does construct wormholes, just not at scales we can see. They might be microscopic, ephemeral, threading the vacuum like tiny threads of geometry, unnoticed by everything except quantum fields. Theoretical physicists sometimes describe these microscopic wormholes as quantum foam, constantly forming and collapsing at the smallest scales imaginable. If this picture is correct, space-time is far from smooth. It is turbulent, riddled with transient connections and evaporating tunnels. But these structures are too small, too brief, and too unstable to have macroscopic consequences. The cosmos builds bridges, but only tiny ones, bridges that vanish before they become real. And yet, the difficulty of forming wormholes naturally raises a deeper question. If nature will not build them for us, could an advanced civilization do it instead? Could intelligence succeed where gravity and quantum fields do not? Now we drift into Part 11. Part 11. Could advanced civilizations build one? If a civilization understood space-time the way we understand bridges and beams, they might sculpt gravity itself. They would need to manipulate negative energy, stabilize quantum fields, and engineer geometry on a cosmic scale. It would be the quietest form of construction imaginable. No metal, no stone, only the shaping of the universe's own curvature. To imagine such a civilization, we must first step back and consider how far our own understanding has come. Just over a century ago, humanity believed space was an empty void, a passive stage on which celestial bodies drifted. Then, Einstein revealed a deeper truth. Space is dynamic. Time is malleable. Gravity is geometry. Suddenly, the universe was no longer a backdrop. It was a flexible material woven with structure and law. Even now, we stand at the very beginning of that understanding. We measure ripples in spacetime with instruments so sensitive they can detect distortions smaller than a proton. We observe gravitational lensing bending light from galaxies billions of years old. We detect quantum fluctuations that shift the vacuum's energy ever so slightly. But these achievements barely scratch the surface. They show us what is possible, not what is yet within reach. A civilization, thousands or even millions of years older, might wield such knowledge effortlessly. Just as a skilled engineer uses tension and compression to build arches, such a species could use curvature and vacuum energy to build wormholes, but the requirements would be immense. The first requirement is negative energy, not merely short bursts of negative energy as seen in quantum fluctuations, but sustained, macroscopic regions of it. To hold a wormhole throat open, a civilization would need exotic matter arranged with extraordinary precision. They might harvest it by manipulating the vacuum, squeezing it the way the Casimir effect does, but on scales vast enough to shape space-time itself. This would demand mastery over the quantum fields permeating the universe. Perhaps they would build devices that create stable pockets of negative energy, shaped like rings or spheres, designed to counteract gravitational collapse. These devices would not be machines in the familiar sense. They would be geometric tools, constructs that reshape the vacuum the way mirrors reshape light. Such tools might be built from ultra-dense materials, superconducting fields, or structures we cannot yet conceive. They would guide and confine quantum fluctuations, smoothing them into stable configurations. The second requirement is a deep understanding of space-time engineering. Curving space-time deliberately is not simply about creating a distortion. It is about maintaining that distortion against disturbances. If a wormhole throat begins to collapse, the exotic matter must respond instantly, expanding, contracting, or shifting its distribution to preserve stability. This implies feedback mechanisms far more advanced than anything we have. It implies that such a civilization would treat curvature as a material, something they can mold, reinforce, and maintain. In our world, engineers stabilize bridges with sensors and counterweights. An advanced civilization might stabilize wormholes with fields that measure curvature in real time, adjusting negative energy densities accordingly. Their wormholes might be lined with layers of geometry, like protective sheaths that prevent collapse from sudden mass influx. Even the entrance might be engineered to funnel objects gently into the throat, minimizing disruptive forces. The third requirement is enormous energy. The energy needed to manipulate spacetime is vast. Even small gravitational distortions require immense power. To shape a wormhole mouth large enough for spacecraft or passengers, a civilization might need to command energies comparable to those produced by stars. They might build Dyson spheres around suns, harvesting vast amounts of starlight. Or they might tap into black holes, using accretion disks as natural power plants. Energy is not the only challenge. Precision is equally essential. Wormholes require perfect alignment between gravity and negative energy, between curvature and stability. Tiny errors could cause catastrophic collapse. The engineering must be exact, down to the smallest detail. A species capable of such accuracy would likely have transcended biological limitations. Machines, quantum computers, or hybrid intelligences might oversee the work, performing calculations beyond human comprehension. How would such a civilization begin constructing a wormhole? One possibility is that they start with a microscopic wormhole, one of the quantum tunnels that may flicker into existence at the smallest scales. Instead of letting it collapse, they stabilize it. They surround it with fields of negative energy, gradually expanding the throat. Like nurturing a fragile seedling, they coax it into a larger structure. The throat grows centimeter by centimeter until it reaches the desired size. This would require tools that can manipulate geometry at the Planck scale, a level of precision we currently cannot approach. Another possibility is that they create a wormhole from scratch, using advanced control over gravitational fields. They might compress spacetime in two regions until their geometries come into contact. They might twist curvature into a configuration where a throat naturally forms. This would be like sculpting a tunnel through the landscape of spacetime, using gravitational engines instead of excavation tools. If they succeed, their wormholes might not resemble the spherical mouths we imagine. They might be shaped like discs, arcs, or rings. The geometry could be optimized for stability, for transport, or for communication. Some mouths might be anchored near stars, others might float quietly in interstellar space. The civilization might use them to span their entire galaxy, creating a network of connections that bypass ordinary distance. Their society could stretch across light years yet remain intimately connected. But the greatest challenge is causality. Wormholes can connect different times as well as different places. If used without caution, they could create time loops, closed time-like curves that threaten paradoxes. A sufficiently advanced civilization might understand these dangers. They might build safeguards to prevent temporal misalignment. They might keep wormhole mouths synchronized or prevent motion that would create causality violations. Or they might embrace temporal engineering, using wormholes not only as pathways, but as tools for navigating time. This raises a profound point. The ability to build wormholes does not simply require scientific mastery. It requires philosophical maturity. A species must understand not only how to shape spacetime, but how such shapes fit into the cosmic order. They must understand the consequences, the risks, and the responsibilities. Wormhole networks could reorganize a galaxy. They could connect civilizations separated by eons. They could reshape history. Given their complexity, advanced civilizations might choose conservative designs. They might restrict wormhole sizes. They might use them only for communication, transmitting signals rather than travelers. A small wormhole, stabilized with minimal exotic matter, could allow instant communication across light years without the dangers of transporting mass. The tunnel would carry information but remain too narrow for objects. Such wormholes, if they exist, would be subtle, unseen, woven into the background of the universe. Or perhaps the civilizations remain hidden. Wormholes might leave faint gravitational signatures, detectable only with sensitive instruments. If such signatures exist, we have not yet found them. But the universe is vast. Our detection tools are young. A civilization millions of years older might sculpt spacetime with such delicacy that their works blend seamlessly into the cosmic fabric. And this leads us to a quiet and profound question. If a wormhole can be engineered, if a throat can be held open and stabilized, then what would it feel like to move through such a passage? Would the experience be violent or gentle, chaotic or calm? Now we drift into Part 12. Part 12. What would traveling through a wormhole feel like? There would be no wind, no motion, no sensation of movement. Inside you would drift along a geodesic, the natural path of spacetime, much like astronauts in orbit. You would move without acceleration. The universe would bend around you, carrying you forward as though you were resting inside a river with no current. To understand this feeling, you must imagine what it means to travel not through space, but within its curvature. The throat of a wormhole is not a physical tunnel lined with walls. It is a region where distances contract, where paths converge, where the standard idea of forward dissolves into the geometry itself. Inside, acceleration ceases to matter. Gravity ceases to feel like a force. You become weightless, not because you are suspended, but because you are falling along a curve that requires no effort to follow. At first, the experience might resemble the calm drift of orbit. But even orbit has subtle tugs. You feel the faint tension of your body adjusting to microgravity. You sense the slight push of air currents, the hum of machinery. Inside a wormhole, none of these cues exist. Silence deepens. Stillness becomes total. Your body does not sense forward motion because there is none. It is the shape of spacetime itself that carries you. As you cross the threshold, the outside universe collapses into distortion behind you. Light bends, colors stretch, stars twist into arcs you cannot name. Then, gradually, even these distortions soften. The throat surrounds you with a geometry that feels less like a space and more like an absence of space, a region where distance loses meaning. You may look outward and see nothing that resembles a tunnel. Instead, you see patterns of light shaped by curvature, faint glimmers reflecting the transition between one region of the universe and another. Your body would feel light, but not fragile. The tidal forces within a traversable wormhole, as imagined in the safest theoretical models, could be engineered or naturally balanced so that physical stress remains low. You would not feel stretching or compression. The space around you would soften its gradients, creating an environment of calm neutrality. You would feel suspended within a gentle equilibrium. And yet, even in this stillness, motion continues. But the motion is not something you do. It is something spacetime does. The geodesic you follow is a natural descent into the throat and back out again. You are not propelling yourself. You are riding the underlying structure of the universe, like a leaf resting on calm water, carried by currents too soft to feel. The passage through the throat might be quick or lingering, depending on the wormhole's geometry. In some solutions, the throat is short, a narrow bridge between two mouths. In others, the interior may stretch into a longer curve, giving you the sense of drifting through an envelope of distorted space. But even if the journey lasts minutes or hours, your senses would not register travel in the way they normally do. Without air resistance or acceleration, time inside the throat would feel like a quiet pause in motion altogether. What you see would depend on the wormhole's structure. In a symmetric, static wormhole, the interior could appear softly luminous, lit by photons that entered the throat and followed curved paths. Some light would come from the universe you left behind, some from the universe you are approaching. These images would overlap, merge, or blur. You might see faint halos, shimmering arcs, and distant highlights. They would not form coherent scenes, but impressions, like Reflections on rippling water, impossible to interpret but mesmerizing to watch. In a rotating wormhole, the interior could twist subtly. Light might swirl gently around you, creating an illusion of spiraling motion even though you feel none. Colors might drift across your vision, shifting in hue as they pass through regions of varying curvature. The effect would not be overwhelming. It would be slow, patient, like watching the sky change during twilight. Your sense of direction would be the first to dissolve. Up and down lose meaning when geodesics converge. Your inner ear would sense no tilt, no rotation, no acceleration. Your heartbeat would steady, your breathing would remain effortless. Even the instinctive awareness of gravity, the subtle pressure that tells you which way to stand, would vanish. Your body would interpret this as a profound stillness, similar to floating in deep water with no waves, no current, no sound. As you drift, the wormhole geometry gently carries you toward the opposite mouth. You might sense a gradual brightening in one direction as light from the destination universe becomes more dominant. Or the transition might be abrupt, the interior distortions simply fading as you emerge into normal spacetime. But the moment of emergence would be quiet, no jolt, no change in pressure, just a shift in the pattern of light. One moment you see the interior's soft haze, the next stars reappear, sharp, distant, familiar. The geometry relaxes, straight lines feel straight again, distances behave, gravity returns as a gentle pull. You feel weight once more as your body reorients itself to the new region of spacetime. If the wormhole's mouths are at different gravitational strengths, the transition might make time feel strange. Not physically, your senses cannot detect the ticking of clocks, but emotionally. You would emerge into a universe that might have aged faster or slower than the one you left. A friend waiting outside could be older or younger relative to what you expect. The stars may be shifted in patterns that suggest time has passed unevenly. Yet your body would feel unchanged. You would have experienced your journey as uninterrupted calm. Inside the throat, time does not stop, but it stops mattering. Proper time, the time you yourself feel, flows steadily. Outside time, the time woven into the universe around you, may not. The two remain connected, but drift apart, like separate rivers with different speeds. This calm drift through geometry is likely the most accurate depiction we can imagine. Not a violent crossing, not a chaotic plunge, not a twisting gravitational storm. Those images belong to black holes, not wormholes. A traversable wormhole, if one could exist, would be engineered or stabilized so that travelers experience minimal forces. Its interior would be designed or naturally shaped to guide you gently along its curvature. The danger would come not from inside, but from instability. A wormhole that collapses while you are inside could expose you to extreme curvature, strong tidal forces, or trapped regions where escape becomes impossible. But in the idealized scenario of a stable wormhole, one maintained by exotic matter or advanced engineering, the experience would be peaceful, eerily peaceful. In this sense, traveling through a wormhole is less like flying and more like falling asleep in a quiet room and waking in another place. The journey vanishes into stillness. You move without movement. You cross the cosmos without feeling distance. And this leads us to a deeper question, one that blends physics with survival and curiosity. If wormhole travel is so serene, what would happen to your body, your ship, and your mind if the throat becomes unstable? What are the dangers tucked into the quiet geometry? Now we drift into Part 13. Part 13. Where would you emerge on the other side? A wormhole has two mouths and a throat connecting them. Where you exit depends on the geometry of those mouths. One might open near a distant star, another at the edge of a galaxy, another in a completely different cosmic epoch. The exit is not chosen by the traveler, but by the shape of space-time itself. To imagine this properly, you must resist the instinct to picture a wormhole like a tunnel through rock or a corridor with two physical ends. In ordinary life, a path leads somewhere because someone built it that way. But in the universe, a wormhole's exit is not constructed in a place. It is a place. It is the region of space-time with which the throat naturally connects. The structure has no preference, it simply follows the solution to the equations that allow it to exist. If the two mouths form naturally, however briefly, however rarely, their positions are determined by the geometry that birthed them. And geometry, in relativity, is shaped by gravity, energy, and motion. Two widely separated regions of space-time might become linked simply because the underlying equations allow it. One mouth could form near a calm, cool region of interstellar space. The other could emerge near a massive black hole, or in the halo of a distant galaxy, or drifting quietly within a sparse cosmic void. If the wormhole is engineered, an advanced civilization could choose where to place its mouths. They could tow one mouth gently to a particular star system. They could anchor another near a safe region far from gravitational hazards. They could even use the wormhole as a bridge between worlds or planets, connecting their society across stellar distances. But even then, the traveler has no control over the exit once inside. The throat is not a crossroads. It is a single, continuous path dictated by geometry. Inside a wormhole, distance loses meaning, but location does not. You emerge where the opposite mouth sits in space-time, because the mouth is not a door in front of you. It is the continuation of the path itself. Consider for a moment the simplest scenario: a wormhole connecting two nearby regions within the same galaxy. You might enter near a quiet red dwarf star. You drift into the throat, experience the calm of its geometry, and emerge in a region perhaps dozens or hundreds of light years away. The stars around you would look unfamiliar. Patterns of constellations would shift. The color of the night sky would change. A traveler stepping out of the craft might not immediately recognize the direction of home, not because they are lost, but because the universe looks different from this vantage. Now imagine a wormhole whose mouths sit not just far apart in space, but far apart in gravitational environments. One mouth might reside near a massive cluster of stars. The other might sit in the outskirts of a thin spiral arm. The brightness of the sky would differ. The density of background stars would shift dramatically. In one region, the Milky Way might stretch richly across the sky. In another, it might appear distant, faint, a thin ribbon among sparse points of light. If the wormhole mouths experience different flows of time, as discussed in earlier sections, the traveler might see a more profound difference. Emerging through the opposite mouth could place you in a region of space that has aged more slowly or more quickly than the region you left. Stars may have evolved differently. A star you remember as a main sequence sun might now be a red giant, or a star that was nearing the end of its life might now shine in its youth, still burning steadily. In the most extreme theoretical cases, wormholes could connect different cosmic epochs. Entering one mouth might take you not only across distance, but across the deep timeline of the universe. You could emerge into a younger universe where galaxies have not yet fully formed, where cosmic dust drifts in dense clouds, or into an older universe where galaxies have stretched thin and grown faint. These ideas remain speculative, but the mathematics does not forbid them. Wormholes do not discriminate between space and time. They connect regions of space-time as a whole. And yet, the most meaningful question for a traveler might be simpler. What would the other side feel like? On emerging, you would feel gravity again. You would sense the gentle tug of the nearest star or the soft pull of a planet if the mouth is anchored near one. You would see the familiar crispness of starlight return, replacing the distortions of the throat. The sky would stop bending, colors would settle. You would know instantly that you have left the wormhole's interior, but everything around you could be new. The constellations would offer no guidance. The galactic core might loom brighter or dimmer. Nebulae might glow faintly or not at all. If the exit is far from any stars, you could find yourself surrounded by a darkness deeper than anything near Earth, cosmic blackness punctured only by distant, scattered points of light. Or you might emerge inside a region dense with starlight, a cluster where suns crowd the sky in dazzling numbers. If a civilization placed the exit intentionally, you might emerge near a station, a beacon, a safely designed region meant to guide travelers. The immediate vistas would reflect their engineering, not nature's whims. The wormhole might be part of a carefully crafted network, each mouth placed in stable orbits around long-lived stars. But in natural wormholes, the exit could be completely uncharted. It could sit in a region where gravity behaves strangely, where radiation is higher or lower than expected, where cosmic dust thickens into veils. The most profound difference, however, might be the sense of irreversibility. Even if the wormhole remains stable, the region you enter is not connected to home by distance anymore. You cannot simply navigate back the way you came. The path home is the path through the throat. If the wormhole collapses behind you, the exit becomes permanent. You stand in a part of the universe you were never meant to reach, at least not within the lifetime of your species. And yet, even if the exit feels uncertain, it is also a doorway to discovery. Every wormhole mouth, no matter how distant, opens into a place where the laws of physics hold true. Gravity still shapes the heavens, stars still burn, light still travels at a constant speed. You emerge into a universe that is unfamiliar, but never hostile by default. The cosmos is vast and varied, but it is always governed by the same quiet principles. The true challenge is not the emergence itself, but the recognition. Once you step out, you would need to orient yourself, mapping the stars, comparing the positions of known galaxies, measuring background radiation, analyzing gravitational fields. Over time, as data accumulates, the region would reveal its position in the grand map of the universe. Even without prior knowledge, the cosmos leaves clues scattered everywhere. And this gives rise to a deeper question. If wormholes can deliver you to any region in spacetime, from familiar corners to distant epochs, can you ever truly know where a wormhole leads before you enter it? This quiet uncertainty brings us naturally to the next question on our journey, one that blends physics with possibility. If wormholes connect far-flung regions of the cosmos, could they connect different universes as well? Now, we drift into Part 14. Part 14. Could a wormhole become a black hole? If the delicate balance sustaining a wormhole fails, the structure collapses inward. The throat pinches shut. Its mass, if any, compresses into a singularity. The passage ceases to exist, replaced by the familiar gravity of a black hole. The universe reverts from a shortcut to a prison of light. To understand how this transformation occurs, you must imagine wormholes and black holes as two potential outcomes of the same underlying geometry. Both arise from the curvature of spacetime. Both represent extreme deformations of the gravitational field, yet one opens and the other closes. One allows passage, the other traps everything that falls within it. The difference lies not in their beginnings, but in their balance. A wormhole demands equilibrium, fine, delicate, constantly maintained. A black hole demands only collapse. A wormhole is the rarest kind of structure in the universe, a shape that bends inward yet refuses to fall all the way through. It requires exotic matter with negative energy density to counteract gravitational collapse. Without that outward push, the inward pull of gravity tightens the throat until it seals. In this moment, the tunnel becomes unstable. Its geometry transforms from a bridge to a well. The graceful curve of the throat pinches into a point, and that point becomes the seed of a singularity. This transition would not feel like a door closing. It would happen on the level of spacetime itself. In relativity, collapse is not a mechanical event. It is the natural response of the geometry to stress-energy imbalance. When the exotic matter fades, disperses, or destabilizes, the inward curvature is no longer opposed. Gravity dominates instantly. The throat narrows, the curvature sharpens, and the wormhole's interior becomes indistinguishable from the interior of a collapsing star. In this sense, wormholes do not become black holes due to failure. They become black holes due to the universe returning to its preferred shape. A wormhole is an exception, sustained by conditions nature rarely supports. A black hole is the rule, the inevitable outcome of inward curvature taken to its limit. The process begins at the throat. As the stabilizing pressure weakens, the radius decreases. Spacetime curves more intensely. Light paths that once wound smoothly through the passage begin to spiral inward, unable to escape. The photon ring tightens, the halos collapse into darkness, the interior geometry grows singular. From an outside observer's point of view, the change would appear gradual but quick, depending on the scale. The mouth of the wormhole might dim slightly as lensing patterns shift. The bright arcs around the throat might distort. Then, suddenly, the mouth becomes a black disc with a glowing ring, the unmistakable signature of a black hole. Light that once escaped through the throat no longer has any path outward. It is pulled into the forming singularity. For a traveler inside the throat, the perspective would be very different. They would feel nothing at first. Wormhole collapse does not announce itself. It does not shake the geometry or produce a sensation of falling. The traveler might still drift along the geodesic, unaware that the tunnel behind them is pinching shut. But as collapse accelerates, the interior structure becomes unstable. Tidal forces would rise. The geometry might stretch in one direction and compress in another. Light around the traveler would redden as the throat contracts, wavelengths stretched by the increasing curvature. If collapse completes before the traveler exits, the throat closes around them. The interior geometry funnels inexorably toward the singularity. Motion cannot escape. Light cannot escape. The geodesic no longer leads to the opposite mouth. It leads inward toward the center of curvature where space-time folds completely. This is the difference between a wormhole and a black hole. In a wormhole, the throat is a passage. In a black hole, the throat becomes a sink. The collapse of a wormhole into a black hole is not merely a theoretical curiosity. It is a direct consequence of the Einstein field equations. The same mathematics that permits a wormhole solution also reveals its fragility. Remove the exotic matter or disrupt its distribution, and the geometry no longer satisfies the conditions for stability. Collapse follows as a matter of necessity, not chance. Some physicists have explored whether collapse always leads to a singularity, or whether certain wormhole configurations might pinch shut without forming one. But in classical general relativity, almost any significant collapse of the throat compresses spacetime enough to create a singularity at the core. Even if the throat contained no matter, the geometry itself can form a singularity. Spacetime does not require mass to curl infinitely inward. It requires only the wrong configuration of curvature. In this way, wormhole collapse resembles the death of massive stars. When a star burns through its nuclear fuel, nothing remains to support it against gravity. It collapses inward, forming a neutron star, or, if sufficiently massive, a black hole. Wormholes follow a similar pattern. Exotic matter is their fuel. When it dissipates, collapse begins. The throat falls inward, forming a region where geodesics converge infinitely. The former passage becomes an event horizon. From the outside, the transition is almost elegant. A mouth that once bent starlight into arcs becomes a sphere of darkness edged by a luminous ring. The gravitational field around it stabilizes into the classic Schwarzschild or Kerr solution, depending on whether the wormhole had angular momentum. No trace of the wormhole remains except, perhaps, subtle anomalies in the surrounding space-time, echoes of the geometry that once existed. If a wormhole is engineered rather than natural, collapse might be slow or abrupt depending on the failure. A gradual decline in negative energy would allow the throat to narrow over time, giving early warning signs detectable by instruments sensitive to curvature. Engineers could evacuate or reinforce the structure, but a sudden fluctuation could collapse the throat far more quickly, with little time for intervention. One question often arises: could a collapsing wormhole be mistaken for a naturally formed black hole? The answer is almost certainly yes. Once collapse completes, the resulting black hole would be observationally indistinguishable from any other. Light cannot reveal its origin. Gravity cannot reveal its history. Only the civilization that built or discovered the wormhole would know its past. This leads to a profound possibility. Some black holes in the universe may once have been something else. Not the graves of stars, but the corpses of failed tunnels, bridges that lost balance and collapsed into permanence. Another question arises: could a wormhole collapse outward instead of inward? In classical physics, no. Collapse always increases curvature. Outward collapse would require the exotic matter to reverse polarity or increase suddenly, pushing the throat open instead of letting it close. But exotic matter is not known to behave in this way. It does not expand explosively. It does not provide outward pressure unless finely controlled. Absent that control, inward collapse is inevitable. Even so, some speculative theories in quantum gravity suggest that wormholes might oscillate before collapse, their throats expanding and contracting like a trembling membrane. But these oscillations, if they exist, would occur at tiny scales and vanish before they could be observed. Ultimately, the transition from wormhole to black hole reflects a deeper truth. The universe favors stability over connection. Bridges require maintenance, tunnels demand support. But wells, gravitational wells, are timeless. They persist, they endure, they require no scaffolding. Collapse is not failure, it is simplicity. And yet, this raises another quiet question. If wormholes can collapse into black holes, could black holes ever do the opposite? Could a black hole, under the right conditions, open into a wormhole? Now we drift into Part 15. Part 15. Why are wormholes the most dangerous shortcuts in the cosmos? A wormhole offers the promise of instant travel, but beneath that promise lies instability, extreme tidal forces, radiation, and the constant risk of collapse. It is a doorway that may vanish as you approach, or worse, while you are inside. The danger is not adventure, it is impermanence written into geometry. To understand this danger, you must begin with the quiet truth that spacetime is not a stable material. It stretches, it bends, it flows under pressure, but it resists unnatural configurations. Every structure in the universe, from stars to galaxies, emerges because the geometry settles into its simplest possible shape. Wormholes are not simple shapes. They are the most delicate configurations general relativity allows. Thin bridges cast between distant regions, held open only by forces that nature seldom sustains. This fragility is the first danger. A wormhole can collapse not because of a catastrophic event, but simply because its delicate balance tips by the slightest amount. The presence of exotic matter must be exact. The distribution of negative energy must remain stable. Even minor fluctuations in the surrounding vacuum can destabilize the throat. A passing star, a burst of radiation, or the mass of a single spacecraft may be enough to shift the geometry. Collapse is not a rare outcome. Collapse is the default. The second danger lies in what collapse means inside the wormhole. In ordinary space, a collapsing building gives warning, sounds, vibrations, shifts that signal danger. A collapsing wormhole gives no such cues. Spacetime folds inward silently. The geodesic you follow narrows without sensation. The path ahead begins to curve toward a region of increasing curvature. And then, at some critical moment, escape becomes impossible. The geometry redirects every possible trajectory inward toward a singularity or a region where motion is trapped. The collapse does not produce heat or shock waves or explosions. It produces inevitability, your path closing around you, the universe tightening into a shape from which no light and no signal can escape. This brings us to the third danger, tidal forces. In a carefully engineered wormhole, tidal forces could be minimized, but in natural wormholes, if they exist, the tidal gradients may be extreme. Tidal forces arise when different parts of an object experience different gravitational pulls. Near a black hole, these forces stretch and compress objects violently. In a wormhole, tidal forces can be just as extreme, depending on the throat's geometry. Even before collapse begins, these gradients might strain spacecraft, distort instruments, or in the case of living travelers, cause biological harm. In the idealized dream of wormhole travel, tidal forces fade into the background. In reality, they loom as constant threats, subtle, invisible, waiting to magnify as geometry fluctuates. The fourth danger is radiation. Wormhole mouths attract radiation the way valleys attract rivers. Light curves inward. High-energy particles follow curved paths. Some spirals deepen. Some strike the throat repeatedly before escaping. These interactions can create concentrated radiation fields. If the wormhole connects regions of different gravitational strength, radiation from one side may be blue-shifted when it enters the throat, intensifying as curvature amplifies its energy. A traveler entering such a region might encounter intense bursts of electromagnetic radiation, X-rays, gamma rays, or exotic particles trapped by curved geodesics. Even if the wormhole is engineered, the radiation problem remains. Negative energy tends to magnify quantum fluctuations, and those fluctuations produce particle-antiparticle pairs. The interior of the throat could shimmer with virtual particles flickering into existence. If these particles gain momentum along certain trajectories, they could become real, generating measurable radiation that accumulates near the mouth. The fifth danger is causal uncertainty. Because wormholes can connect regions of spacetime with different gravitational potentials or different velocities, time may flow differently at each mouth. Enter a wormhole from a region of slow time and emerge into a region of fast time, and you find the universe has aged more rapidly than expected. Reverse the journey, and you may step out into an earlier cosmic moment. This temporal misalignment does not create paradoxes by itself, but it creates a profound risk. Miscommunication, miscoordination, and the unpredictability of outside conditions. A wormhole mouth placed near a star that later evolves into a red giant could expose travelers to unexpected hazards. A mouth placed in interstellar space could drift over millennia, or an entire region of the cosmos could shift gravitationally or collapse before a traveler returns. The danger is not violence, it is unpredictability written into spacetime. The sixth danger is mass accumulation. If matter collects near the throat, dust, gas, stellar debris, it can destabilize the geometry. Black holes grow by accreting mass. Wormholes collapse under it. A steady flow of particles, even sparse ones, can gradually alter the balance between inward and outward curvature. Over long durations, this mass accumulation can trigger collapse. A wormhole mouth that has remained stable for centuries might collapse suddenly after collecting enough interstellar dust. This danger grows in environments with dense radiation, strong gravitational waves, or debris from stellar winds. A wormhole mouth drifting near a supernova remnant, for example, would be exposed to relentless influxes of high-energy particles. Each particle adds stress, each photon adds curvature. The throat grows narrower bit by bit. The seventh danger lies in quantum instability. Quantum fields permeate all of spacetime. In ordinary regions, their fluctuations average out. Near a wormhole throat, they do not. The geometry amplifies some fluctuations, suppresses others, and creates feedback loops that can escalate unpredictably. A tiny fluctuation in vacuum energy can grow exponentially. A small increase in negative energy density can destabilize the entire structure. Even quantum noise, subtle, random, invisible, can nudge the throat toward collapse. Some physicists believe this instability is not a flaw, but a fundamental truth, that nature protects chronology by resisting wormholes. Under this view, wormholes collapse whenever they approach configurations that allow time travel or causality violations. Radiation floods the throat, stress energy diverges, collapse becomes unavoidable. A wormhole becomes the most fragile of all cosmic objects, safe only when unused, dangerous the moment it becomes a transportation link. And this leads to the most profound danger: impermanence. A wormhole has no guarantee of longevity. It might remain stable for minutes, hours, centuries, or fractions of a second. A traveler could approach it cautiously, study its curvature, estimate its stability, only to have the throat collapse in the instant before entry. Worse, the collapse could begin after entry, trapping them inside the geometry. Time dilation might stretch the experience, or curvature could compress it into a sudden silent endpoint. A wormhole is not a highway. It is a delicate alignment of the universe's laws. To travel through it is to trust forces that even the most advanced civilizations may not fully control. Yet the danger does not negate the wonder. A wormhole is perilous precisely because it lies at the edge of what the universe permits. It is a brief opening carved into the cosmic fabric, a temporary reversal of spacetime's deepest instincts. To approach one is to stand at the boundary between the known and the unknown. To enter one is to surrender to geometry itself. And as we drift deeper into this quiet journey, one final question rises from the shadows of physics and possibility. If wormholes are so fragile, dangerous, and easily lost, why do they continue to fascinate us? What does their mystery reveal about our desire to cross the boundaries of the universe? The universe is vast beyond measure, yet its deepest mysteries are often hidden in the smallest folds of its fabric. Wormholes, if they exist, are not the grand glowing tunnels imagined in stories. They are fragile arrangements of curvature, brief alignments of geometry, places where distance softens and time bends into unexpected shapes. They remind us that the cosmos is not a rigid structure, but a living landscape, flexible, dynamic, shaped by energy and motion in ways our senses can barely understand. As we traveled through these ideas tonight, we drifted across the quiet edges of physics. We followed the equations to places where the universe almost allows shortcuts. We traced the delicate balance that keeps a wormhole open, the dangers that follow if it collapses, and the strange beauty of a passage that connects regions separated by impossible distances. And in all of it, one truth lingers gently. The cosmos holds far more possibilities than we can see from our single place in it. Even if wormholes remain theoretical, the wonder they inspire is real. They invite us to imagine a universe where connection outpaces distance, where the night sky becomes a map of hidden paths, and where the very fabric of reality can rearrange itself into something unexpectedly open. They ask us to consider not only what the universe is, but what it could be. If this quiet journey offered you even a moment of peace, I'm deeply grateful you were here. Your gentle like, your soft tap on subscribe, and your presence mean more than you know. Thank you for spending your night among the stars. Now, as the thoughts settle and the universe stretches out around you in its ancient stillness, may you rest deeply. May your breath slow. May your mind drift. And may sleep take you as softly as gravity guides a falling star along its natural path. Good night.